Assalamualaikum everyone and a very good day to all. In this video, we shall learn about time division multiplexing or TDM, which is one of the basic techniques of multiplexing. Here is the table of contents for you to navigate through this video. This video is the continuation from TDM video part 1. Okay, let's quickly recap about TDM. TDM is a digital process that allows several connections to share the high bandwidth of a link. Each connection occupies a portion of the time in the link. Note that the link is sectioned by time rather than by frequency, where the portions of signals 1, 2, and 3 occupy the link sequentially. We can divide TDM into two different schemes, synchronous and statistical. In this slide, we can see the concept of synchronous TDM. Synchronous TDM is called synchronous not because synchronous transmission is used, as we learned in chapter 4, but because time slots are pre-assigned to sources and fixed. If you remember, in synchronous transmission, bits are sent one after another without start or stop bits or gaps, and the receiver will group the bits. Okay, back to synchronous TDM. The time slots for each source are transmitted whether or not the source has data to send. This is of course also the same case with FDM. In both cases, capacity is wasted to achieve simplicity of implementation. So there is pro and cons. The cons is there is some wasted capacity, whereas the pro, it is simple to implement. Even when the fixed assignment is used, however, it is possible for a synchronous TDM device to handle sources of different data rates. For example, the slowest input device could be assigned one slot per cycle, while faster devices are assigned multiple slots per cycle. We shall see this example in the next video on data rate management. Bear in mind, in the previous and upcoming examples so far that we have, the scale of the duration is not in scale, but in this figure it is in scale. Okay, just to show you the difference, meaning to say that in this figure the representation of the data prior to multiplexing is 3 times the size of the data after multiplexing. This is just to convey the idea that each unit is 3 times longer in duration before multiplexing than after. Okay, the next few examples are still under synchronous TDM, and then we shall see statistical TDM differs in the next video. Okay, in this example, a synchronous TDM is shown with a data stream for each input and one data stream for the output. The unit of data is 1 bit. Find A, the input bit duration, B, the output bit duration, C, the output bit rate, and D, the output frame rate. Again, bear in mind that the duration or T in this figure is not to scale. We can answer the questions as follows. For A, the input duration is the inverse of the bit rate. Okay, so 1 over 1 megabit per second equals to 1 microsecond. For B, the output bit duration is 1/4 of the input bit duration. Since we have 4 inputs, so T over 4 equals to 1 microsecond divided by 4, which equals to 0.25 microsecond. For C, the output bit rate is the inverse of the output bit duration, or 1 over 1 over 4 microsecond, or 1 over 0.25 microsecond, which gives us 4 megabit per second. This can also be deduced from the fact that the output rate is 4 times as fast as any input rate. So the output rate is 4 times 1 megabit per second, and you shall get the same answer, which is 4 megabit per second. For D, the frame rate is always the same as any input rate. So the frame rate is 1 million, or 1 times 10 to the power of 6 frames per second. Because we are sending 4 bits in each frame, we can verify the result of the previous question by multiplying the frame rate by the number of bits per second. Now I want you to try this yourself and see if you can get the answer. Assume that the data rate for each input connection in figure above is 5 megabit per second. A unit is 1 bit. Find the new durations for A, the input bit duration, B, the output bit duration, C, the output bit rate, and D, the output frame rate. Next, let's go to another example. Here we have 1 kilobit per second connections and they are multiplexed together. A unit is 1 bit. Find A, the duration of 1 bit before multiplexing, B, the transmission rate of the link, C, the duration of a time slot, and D, the duration of a frame. As you can see, so far all the examples are using 1 bit as the unit size. We will see some example in the next video where the unit size is not 1 bit. Also, you can notice that typically the question are asking you about the duration and the rate. So just make sure that you understand that the rate is the inverse of duration, so you'll be fine. We can answer the question as follows. For A, the duration of 1 bit before multiplexing, meaning the input bit duration, is 1 over 1 kilobit per second or 1 millisecond. For B, the rate of the link is basically 4 times the rate of a connection. By connection, it means that the input rate before the multiplexing. So you shall get 4 kilobit per second. For C, the duration of each time slot or the output bit duration is 1/4 of the duration of each bit before multiplexing, or in other words, input bit duration is 1 over 4 kilobit per second or 250 microsecond. Note that we can also calculate this from the data rate of the link, 4 kilobit per second. The bit duration is the inverse of the data rate, or 1 over 4 kilobit per second, which will get the same answer, 250 microsecond. For D, the duration of a frame is always the same as the duration of a unit before multiplexing, or 1 millisecond. We can also calculate this in another way. Each frame in this case has 4 time slots, so the duration of a frame is 4 times 250 microsecond, or you shall get 1 millisecond. Again, don't forget to try this with a new assumption, which is 1 kilobit per second instead of 4, and see whether you can get the answer for A, B, C, and D. Before I end this video, let's discuss interleaving. TDM can be visualized as 2 fast rotating switches. One on the multiplexing side and the other one on the demultiplexing side. The switches are synchronized and rotate at the same speed but in opposite directions. On the multiplexing side, as the switch opens in front of a connection, that connection has the opportunity to send a unit onto the path. The connection could be the top string or input A, then the middle or the input B, and lastly the bottom string or input C. This process is called interleaving. On the demultiplexing side, as the switch opens in front of a connection, that connection has the opportunity to receive a unit from the path, so it will receive sequentially. This figure shows the interleaving process for the connection shown in example 1 in the previous video, as well as the one in slide 4 in this video. Or you can see at the top middle figure as well. In this figure, we assume that no switching is involved and that the data from the first connection at the multiplexer side go to the first connection at the demultiplexer. The interleaving can be at the bit level or in blocks of bytes or larger quantities, not necessarily at bit level, 1 bit. Okay, with this interleaving, we can have a different number of bits per unit. For example, one interleaving unit, there can be 2 bits or 1 byte or 1 character and so on. Since each frame contains a cycle of time slots, in each frame, one or more slots are dedicated to each data source. We shall see more examples of this in the next video. Before I end this video, please let me know how is your understanding on this topic throughout this video so far at this link. Your participation is highly appreciated. If you have any questions or comments, please let me know. Thank you and see you on the next video.